Okay, so what I want to do real quick is just kind of go over what the idea of systems programming even is to begin with, because there seems to be a lot of I guess, confusion on just what the concept of it is to begin with. Because some people say, oh, it's like embedded programming, or it's anything low level with the kernel access, or anything of that nature, or there's some huge difference between basic C, system C specifically, as if though that's a different language, and just anything like that. So there seems to be just a little bit of confusion in terms of what the actual scope of systems programming in general is. So without further ado, let's just go ahead and swap over the slides real quick and just take a look. So again, just the idea of what is this? Like, what is systems incorporated in programming essentially? And there's honestly several definitions for it, but if I had to really nitpick anything, is the kind of the layer in the software hardware stack that you are. So real quick, everything that almost any definition deals with is pertaining to the operating system, whether that be writing or modifying them. So like if you're writing a Unix operating system like Linux or Mac OS, or even writing Windows or whatnot, or even just using the various APIs that those operating systems use, that is some form of systems programming. You are at the operating system level. So again, if we look in these two images here on the right, you have two distinct images, but they kind of tell the same story. And again, it's in that layer of the software stack and hardware stack that you are. So a lot of what people, when they get introduced into programming, they get introduced into application software. Whether you're making games, obviously you're not making something like Microsoft Office, that's a massive program, or Adobe Photoshop. Maybe you make a basic calculator or something, just some basic GUI application, maybe a command line application. It doesn't matter how complex it is, it's in the application layer that most people, most users are familiar with. You're not dealing with the actual operating system itself, any of its actual API calls and whatnot that are very particular to that operating system. So systems programming just deals with the operating system and not the layer that is on top of that. So what that really means is the most common desktop operating system is Windows. Most people are not using Windows because they like Windows. They like the software that runs on Windows. They like the applications that run on these operating systems. If you were left to your own devices and you didn't have the application layer, nobody would really care on the Windows side very much, because there's not a whole lot there. Most people that are using that are using it for the applications that run on top of it. Whereas if you're in the Unix world, specifically in the embedded programming aspect, you're used to being in the operating system layer quite heavily. Now when you get to Mac OS, that is definitely more a departure from that layer. You're getting more into the application style of things. So it's kind of different there. But when you do a lot of, and this is why embedded development gets in there, you are almost always at the operating system level. That'd be the kernel level, the API level, all those different things. You're almost always in this bubble here. Very rarely do you get to the application software layer, and most people in software development are not at hardware level. You might be if you're doing serial devices and stuff like that. Some people get further down if you're doing assembly and whatnot. You kind of are here, or a lot of time on the bottom one, a lot of people do hardware with drivers and whatnot and those serial devices. And being able to deal with this layer of software is really, really nice. Whether that be if you're doing networking is another huge part for dealing with your operating systems, APIs and whatnot, is dealing with the actual networking that is native to that operating system. Kernel, if you're doing Linux, that's the Linux kernel, and that gets into its own headaches and whatnot of where does the kernel start, where does it end, depending on what operating system you're on, what type of kernel you have. In terms of systems programming, it can be almost anything in between the hardware and wherever the application layer would start. So it's kind of a broad scope of things, but generally, if what you're programming is specific to the operating system that you're running, that's some form of systems programming here. So we're going to be doing Unix because it is, without a doubt, the most widespread operating system in the world. You might say, hey, on the previous slide, we said that Windows was the most common desktop operating system. And that's true. On the desktop, or what people use in their laptops and their work devices and stuff like that, Windows is by far the most common operating system. Even if we include Chrome OS or Mac OS and all those different things, it is Windows dominated very strongly. However, when it comes to all devices, it's not just Linux and Mac OS and Google Chrome or Chrome OS that people are paying attention to. Then you get servers and supercomputers. Your phones, Android and iOS, are both the Unix-based operating systems. So then you also get routers and other smart devices, Raspberry Pis, almost all the embedded devices, almost all of these different systems are all using some form of Unix. Very often it's some form of Linux, but not always. If you look at some very common consumer devices like a Nintendo Switch or a PlayStation 4 or 5, those actually run on a free BSD based operating system. So now BSD gets into here. People very, very familiar with MacBooks and iPhones and stuff like that, iPads. Those are all in Mac OS. Now, if you look on the right side, there's like a whole timeline of things. You get the BSD family, Unix starting over here in Bell Labs and whatnot, commercial AT&T and whatnot, Solaris, rest in peace, HPUX, IRX, and eventually you see Darwin spawns off with Mac OS off of Next Step. Whole history there. It's quite a lot. You actually not notice Linux is over here on its own thing, starting from GNU, which does not really technically originate from Unix, because some of these are not exactly Unix. They might be Unix-like. I think the only real popular existing Unix right now by the license and technical definition is Mac OS, and even then it has its own deviations from original Unix and whatnot. Linux with its own spawn from Minix and whatnot. And again, there's a whole history of things. But all of these work under that same type of principle. They all follow the same standards usually. Far closer than Windows and their NT kernel and all the things that Microsoft has done. So those two are like your most common splits when it comes to operating systems. There are other ones, but Unix is a very common target for systems programming because it's very widespread. On that note, the language of choice here that we're going to use is C, which is a very old language, but most operating systems are written in C. Most kernel stuff is done in C. Very, very low level application, embedded devices stuff is done in C. If you're on Windows, you can actually do a lot of systems programming in .NET, like C# and whatnot, because that's kind of some of the core utilities that you would use there. So again, there are some differences between what environment you're in. So again, no Windows, not gonna be an issue here. Because if you happen to have Mac OS, Linux, if you happen to have a running instance of BSD, I have a few, you could use that. As long as you have access to a basic C compiler on a Unix system, or a Unix-like system like Linux, we are good to go. So if you're on Windows, I have a video setting up WSL2, which is a Windows subsystem for Linux, and that actually implements a completely virtualized Linux operating system with like a full feature-rich kernel. The reason I'm saying that is because WSL1 does not do that. It is not it's not its own actual entirely separate existence. It kind of has a hybrid kernel going on, and it doesn't function properly under a lot of Linux system calls and Unix system calls because it's got some hybrid environment with Windows, so it's not exactly a proper solution here. You would need an actual dedicated virtual machine, whether it be VirtualBox, VMware, or WSL2 specifically, for this to be okay, because those are isolated to the Linux kernel and those system calls will work just fine. So if you need to get that set up, I have a different video for it. I'll have it probably linked in a little title at the top, so not a big deal. Now, for the language, C. It's a very common systems language because most operating systems are written in it. So all your libraries and everything, you're going to be coexisting there. And that's perfectly fine. So it's a very, very concise language. It is very old. It is over 50 years old now, so it has some age issues, some teething issues for a lot of developers, and there's a lot going on. So again, a lot of what we'll focus on is going to be file I/O, threads, child parent processes. We won't really touch on the networking too much. You would have to take like a data communications class to deal with some of that networking and whatnot. A lot of what we will deal with here is kind of a precursor to that networking experience, but it's not going to be something we super focus on. So, this part right here, signal and thread safety. This is where a lot of people try to make a differentiation between, oh, you're programming in C versus programming in System C. There's no real such thing as System C. There are functions and system calls that you should and should not use depending on if you're doing signal-based programming or multi-threaded programming. If you're doing things like your standard printf, scanf, string TOK, a lot of the string functions, or some of the older string functions, A2I, which is built off string TOK, things like that, those are not acceptable because they are not considered to be signal safe. They are not thread safe, and it's not memory safe specifically. So the moment you start trying to throw in multiple processes, whether that be through threads, whether that be through signals, when you have things that have static buffers, it causes race conditions and things can get out of order very, very quickly. When you do with printf, scanf, those have file pointers, and if you try and do it across multiple actual threads and whatnot, you can run into all sorts of issues. So very commonly, we have this man page here of signal safety that has a long list of valid functions that are okay to be used, but even some of them you have to actually pay attention to what compiler am I using, what's the age of said compiler, are some of these functions even present in the actual compiler I have. So if you have like a C99, some of the POSIX compliant functions that were made in 01 or 08 and stuff like that, they may not be available. So you have to be kind of careful on what you are and what you're not using. And a lot of that just comes down to looking at the resources you have and doing proper research on doing multi-thread programming. Is this function okay? Because certain ones will have a more modern version of that function that can have a buffer length that is taken into account, so you're not doing buffer overflows and whatnot. So certain functions have maybe 4 or 5 different variants, and maybe one of those newer variants is okay. A really good example of that is string TOK. This is not acceptable, but string TOK _R, that one is acceptable. There is an actual aspect added to this system call that makes it okay to be used in signal-based programming. And they recognize, hey, there are issues, there are bugs that happen if you try and do, anything with multiple threads, processes, and stuff like that. So we need to make a revision on this. We're not going to get rid of the old one for compatibility's sake on legacy software, but if you're going to do anything moving forward, you need to be using this version of the function. Or if making any revisions to your old software, you should probably change from this version to the new version. So another one of those would be like sprintf, I think has a revision of sn printf. And this n, a lot of these actually is, I think, stands for number. And now it lets you actually specify a number of bytes that you want to print to the user, and it prevents you from getting buffer overflows and whatnot. So lots of revisions of existing functions and system calls happen, and it's just a matter of making sure that you are using something that is not going to cause abnormal behavior. So it might do what you want most of the time, but the moment that this and this happens, signals and multi-threading, they can cause undefined behavior. They can cause just a variety of problems. fopen, fclose, fread and write, stuff like that, anything with buffers and whatnot like that, are also heavily disallowed. You're going to be looking at your very low level write, open, read, write, open, close. Actual system calls from the operating system layer that deal with file descriptors rather than file pointers. So this idea here, this whole process here of not being allowed to use certain functions due to thread and signal safety is where you get the idea of system C from. And really all you're doing is trying to be memory safe. So it's not really a difference between C and system C. It's just you need to be careful and try to write actually memory safe programs. Still C, but it's C with restrictions essentially. And then finally, all of this, we have the idea that C is a compiled language. A lot of people that are programming here have already done C++. However, you probably used Visual Studio Community, Qt Creator, maybe Xcode if you're on macOS, and you use an IDE that handled a lot of the actual compilation process for you. This is where you have to get used to using the actual separate compilers like GCC for Linux, CLang, or Clang for macOS. And you have to understand how compiling code works, especially when we get to multiple processes, because if we get into like FIFOs and whatnot, or execvp system calls and stuff like that, you're going to need to actually take multiple files of source code and create multiple binaries, and some of those binaries might call other external programs. So you can't just say, oh, here's all my C files and my header files, I'm going to compile all of them into one giant binary. And that's not how it works all the time. Sometimes you need to make multiple binary executables and work with them in tandem essentially. So this is where you have to understand the process of compiling applications. Another thing is doing command line arguments. When you're doing IDEs and whatnot, you generally don't get that. You're used to running the application and then using something like cin or scanf or something like that to read input from the user during runtime. And that's not something you do frequently when it comes to systems programming. A lot of the time what you do is you type out your binary executable in your terminal, and then you type in multiple arguments or parameters that will be sent to the actual application the moment you run it, and those are going to be your command line arguments. So you're going to pass those in as an argument vector to that application. So this is kind of an entire different paradigm of interfacing with your code and the application itself, and understanding that from a kind of a top to bottom aspect, as opposed to I write my code in my IDE text editor, I hit run, and then I just let things go. That's not gonna cut it here. So that's kind of where we are for this class and what the expectations are here. So I do hope all that made sense, and I hope that kind of clarifies what exactly systems programming is, why there's really no such thing as System C versus regular C, and just kind of clarifies a lot of what we will get to in later videos, later assignments and stuff like that. And mostly, honestly, I just hope this was a helpful video, so if it is, that's good. If it's not, I will hopefully try to clear up any misunderstandings or confusion along the way. Anyway, that's all I got. I'll see you next video. Bye.